ماذا لو أن الكفاءات الجزائرية من كافة أنحاء العالم تجتمع معاً؟ ماذا لو أن هذه الأدمغة بمختلف تخصصاتها تتكاثف لتطوير التعليم والبحث العلمي للنهوض بالجزائر في مختلف المجالات؟ هل تعتقد أن هذا مستحيل؟ أبداً، فالحلم يتحول إلى حقيقة من خلال الشبكة العالمية للعلماء الجزائريين إيناس. رغم أن إيناس هي مؤسسة غير ربحية وتعتمد فقط على تبرعات الأفراد، إلا أنها استطاعت أن تبني جسوراً من التعاون وتبادل الخبرات بين أبناء وطننا الحبيب من الداخل ومن مختلف بلدان العالم، ساعية لصقل المهارات واحتواء المواهب وتبادل الخبرات وإيصال التجارب النافعة لخدمة الوطن.
Hello everyone, welcome back to Inas. Hope everyone is doing well. Welcome to a new episode in our new program, which is about artificial intelligence in neurosciences. So today's speakers, we have Dr. Mohamed Amrouche. For those who already followed the program of geosciences in Inas, already familiar with him. So welcome, Dr. Mohamed. Thank you for accepting to share with us your insights today and your experience.
Thank you.
So Dr. Mohamed is geophysicist from SLB and who has an experience in Japan, and now he works in Algeria. And without taking any longer, so I will give him the mic to share with us his presentation.
Thank you very much, Ahmed. I think before starting, I just would like to be sure that everything works well. Can you please let me know if you can see my slides and you can see my pointer?
Of course. Yeah, I can see the pointer, the slides also.
Okay. So, we can start, I think. Thank you. So, Assalamu alaikum. Good afternoon or good morning, everyone. Thank you very much for joining us in this new webinar titled Accelerating Seismic Interpretation Using Machine Learning in our new initiative, Advanced of Artificial Intelligence in Geosciences. So in this project, we will try to promote and share with you what is being done in artificial intelligence for the geosciences. And today's presentation, we are especially going to tackle seismic interpretation using machine learning. So this is my presentation today, the outline of my presentation. We start with discussing what are seismic interpretation, the conventional seismic interpretation workflows, what I call semi-automated seismic interpretation, and for a global vision for the people who are not working in the industry, what is happening in the oil and gas industry, what is the digital transformation. We also discuss the new machine learning algorithms, machine learning-based seismic interpretation, and see some demonstration case studies on how machine learning can help us to accelerate for fault detection and horizon interpretation, and finally share with you some published case studies using this new technology from SLB. Okay, so starting with the conventional seismic interpretation workflows. So what we mean by conventional seismic interpretation workflows is what usually geophysicists do on their daily basis, okay? It is one of the most time-consuming processes for the subsurface characterization. It can take weeks, months, or sometimes years of work. Geophysicists need to spend a lot of time doing fault stick interpretation, horizon interpretation, and this can be a really, really tough job that can take a lot of time. So interpreting seismic structure and geological features such as fault, horizon, and geobody requires a lot of attention and accuracy, as well as expertise. And as seismic interpretation is knowledge-based and experience-intensive, obtaining an accurate interpretation requires significant expertise. So we have a lot of models, and each model will be representative of his own interpreter, basically. Okay, so if we have to break down the classical seismic interpretation workflows, for those who are not familiar with it, it starts with the 3D seismic data or 2D seismic data. So we need to do some seismic data conditioning of the post-stack seismic data. We do some cropping, realization, denoising, and then we start doing some manual interpretation of the faults. We start with the seismic well tie, while we're going to generate synthetics along the well and try to tie the seismic data with the wells, and then using a 3D interpretation workflows, we are going to do manual fault interpretation stick by stick, and then horizon fault interpretation, calculate some seismic attributes, and then finally cross-check the interpretation results to finally integrate the interpretation workflows into the model. We have also what we call advanced seismic interpretation. This is basically using rock physics properties based on generating some deterministic seismic interpretative targeting by doing some inversion. We can extract geobody using seismic inversion of the reservoir or some specific shapes such as channels, and then integrating them into the model. So this is what I mean by the classical seismic interpretation workflow. This is what we've been doing, and this is what we are doing now as geophysicists. So the problem with this process is that it takes a lot of time, it takes a lot of work. What I mean is that starting from one single seismic cube, you will have a team doing some major fault interpretation. Some other geophysicists are going to do minor fault interpretation, and each geophysicist will have his own model. And then we start building models based on these interpretative models. And then when we move forward in the reserve modeling workflow, we are going to end up with many models, different models with integrating different interpretations that can be really, really misleading at the end of the day. So this can need to be reiterated sometimes. We need to go back to the original seismic data, try to understand what went wrong, try to correct the model, moving forward, and then going in cycles. So this can be really frustrating for decision making for people who are doing reserve estimations, especially geophysicists who are having different results. Basically, this can take days to weeks of work. So automating this workflow can be a really a dream, I would say, for people who are working in this. Okay, and here we come. What we call we already have some existing solution in the industry that can help to partially automate the seismic interpretation workflow. This is what personally I call semi-automated seismic interpretation workflows. So, of course, in this presentation, I'm going to talk about Petrel. Okay, so for example, if you take Petrel, we start with the seismic data, you do manual horizon interpretation. We have what we call, seeded auto tracker, 2D seeded auto tracker, 3D seeded auto tracker. This can be very powerful tool to help you to quickly do a horizon interpretation, for instance. And then you can use seismic attributes, okay, to enhance the quality of the faults, the contact and the faults, and then extract them using the end tracking. And then why not correcting the end tracking manually and create your faults. So this is what I call the semi-automated, because it's still based on manual processes. We do have other examples. For example, we can take the neural network trained model. Let's say this is your input data. You can see you have some kind of channel here, a geopody channel that you want to extract from the data. Then we're going to calculate some seismic attributes, different attributes that we are going to correlate using or classify using a neural network classifier in Petrel. And we are trying to estimate or predict the existence of the channel inside the model and extracted it using the geobody extractor. I apologize for the blurry picture because I'm not sure about the show rights of the data, but just think about it. It can be a channel, it can be a reef, it can be any geological body or geobody, and then you can use it to extract the neural network. Another method less known by the engineers in the industry is what we call the self-organized maps or seismic wave classification. It's based on the Conan 3D mapping and classification. Basically, you are going to clusterize and classify the seismic amplitudes that can give you some specific features or highlight some specific features automatically and extract them from your seismic data. So as you can see, the industry already have some kind of keys or some kind of elements that can help you to slightly accelerate or to enhance the interpretation of the seismic workflows. All right, now let's take a wider look. I would like to talk a little bit about what is going in our industry, in the oil and gas industry. A few years ago, and let's say like 5 to 6 years ago, we started talking about the digital transformation in the energy industry. What we mean by the digital transformation in the energy industry, basically, to make it simple, nowadays the easy oil time has ended, and the energy sector is undergoing major transformation. So we are not finding huge oil reserves and gas reserves like we used to do 30, 50 years ago, but rather we are trying to explore a little bit more details of the existing reserves and try to maximize the profit and maximize the production of the oil and gas. And in order to enhance this, we are trying to take advantage of the existing technology, especially AI, artificial intelligence, cloud computation, that can help us to automate and accelerate decision making using smart workflows that are used in the cloud, for example. For instance, just to give you numbers, AI technologies breakthrough in numbers. So where portfolio optimization was reduced cost and time over 85%. The seismic fault interpretation and horizon interpretation was reduced 80% of the time. So as you can, this is what we are going to discuss today, by the way. And petrophysical log interpretation was automated up to 90%. So can you imagine all the log interpretation and correlation workflows are going to become automatic, right? So this is a huge transformation in the industry. A lot of work is being done, a lot of investment is being put. As you can see, the digital oil field market worth is 34.5 billion by 2026. A collaboration between Microsoft, Chevron, and Schlumberger, now SLB. The COVID-19 also accelerated the migration of the energy sector to the digital and automation. Now we are more keen on using the cloud, using the remote work, etc. So the COVID-19 really pushed forward the adoption of the digital transformation in the oil and gas. Right. So in this context, SLB or Schlumberger developed our own digital cloud platform. It's called Delphi. It is a secured cloud-based platform providing a common space for teams and working together for borderless collaboration. Think about it as a remote virtual machine on the cloud where you just need your password and your username, and you can connect from any device and run really, really complex calculations. You can take your tablet, you can take your laptop, and your data are on the cloud, so you can take the advantage of a high-performance computing, use different Schlumberger software and the same the access, and collaborate in real time with your colleagues without moving from your seat. Okay, so the platform SLB Delphi already have the domains, all the softwares coming from Petrel, Techlog, Olga, PipeSim, OFM, etc., all available on the cloud, and you can access them really at your fingertips. Okay, so you just need, as you can see, log into the Delphi portal, select your subscription if you're a geologist or geophysicist, and then start working remotely on your complex data using the cloud environment from your house. Okay, this is really a game changer, I would say. Your workspace is always in reach when your workstation is not. You can collaborate and cross teams with a high-performance 3D session sharing, and also you can unlock limitless elastic cloud computation by parallelizing a number of CPUs and run really, really complex computations that you usually need specific hardware to do. Okay, now talking about this, let's see what machine learning can offer us in this perspective as geophysicists. And this is where I'm going to talk about the new generation of machine learning-based seismic interpretation. We've been listening about the machine learning for 4 years now. Everybody's telling machine learning, but really, as I say, the honeymoon season is over. We need to we need to see real results. We really need to see how the machine learning is going to change our way of doing things. Okay, and this is where the novel generation machine learning ML-based seismic interpretation can show a really good example on how machine learning can change the daily work of geophysicists, for instance. Okay, before talking about machine learning and seismic interpretation, let us just debrief some terminology. Let us just be okay on determining some terms. Okay, there are many words around here, not sometimes or often not properly well used. So let's try to debrief that, and first starting with some terminology. So we have what we call an artificial intelligence, AI. Okay, AI means any technique which enables computers to mimic the human behavior. It started back in the 40s to the 50s. Where the machines started helping humans in their factories, manufacturing stuff. And then we have what we call machine learning, the ML. The machine learning is a subset of artificial intelligence techniques, which is used statistical method to enable machines to improve with experience. Okay, after a model has been suitably trained, it can then be used to predict similar patterns in data it has never seen before. So the particularity of the machine learning is that it's going to learn, it's going to enhance itself, rather just applying, automatic workflows as in artificial intelligence. And finally, we have what we call the deep learning. So the deep learning is just a magical word, I would say, but it's just a subset. It's a type of machine learning which makes the computation of multi-layers neural network that goes beyond 3 layers feasible. So it's a deep learning because the learning layers of the machine learning is deep. It's over 3 layers, and it takes a little bit more time of computation, I would say, that gives better results, basically. So the machine learning is not something that is dating from now. This is very important to keep in mind. I saw some people thinking that this is a new technology. No, this is not a new technology. Artificial intelligence back to the 40s. Some people trace it back to the Enigma machine when Alan Turing breaking the Enigma machine during the World War II. For example, in 1951, Prince develops the first chess program, based on artificial intelligence. In the 80s, you have the IBM in 1997. the computer IBM Deep Blue beat Gary Kasparov, one of the champions in the chess, for example. In 90s, between 90s and 2000, for example, in 2004, NASA developed the Opportunity rover that automatically navigates in the surface of Mars based on machine learning. So the robot is going to learn itself and predict the moves and try to improve its move. Now, talking about the deep learning, it's really started in booming, in the 2010s, with the democratization of AI, where we are using all the platform using artificial intelligence. For instance, we have in 2018 deepfake technology, and more recently, talking about generative AI and ChatGPT and all this very, very powerful generative tool based on the deep learning or the branch of machine learning. Now, the interesting story with this is that there is another backstory with this evolution, is the hardware improvement. So between 1960, we used mainframe computing, and then we start using CPUs in the 70s, and then in the 90s as GPUs. Now we are using cloud computing, and you see that this evolution actually is driven by the power of the hardware we are using, right? So this is really something not new, okay? Now we are talking about the democratization of the AI, mainly because of the powerful computers we have and the huge amount of data. It's the age of data, the data set we have that we can use to predict better patterns, I would say. And also, I don't know what's going to advance it with the quantum computing. When we unlock the quantum capability of the computers, I'm pretty sure we are going to see a whole new technology based on machine learning in the near future. Okay, so let's try to take advantage of this machine learning and try to automate all the boring process I discussed before in seismic interpretation, how we can automate, fault interpretation, horizon interpretation based on machine learning on the cloud, okay? So we can use a secure cloud-based fast computation and large storage, for instance, talking about Delphi, SLB's Delphi, okay? Of course, also we can use seismic data to train predictive models. So the machine learning is based on learning patterns, so we need to train some kind of virtual brains, I would say, using data sets. So we can use public seismic data just to train and give more accuracy on the prediction. And finally, directly connect to the modeling and really spend more time on the geology, rather spending more time on doing fault stick analysis, fault stick interpretation and horizon point clicking. So you can see that with machine learning on the cloud, we can shrink or we can reduce the cycle of interpretation from months to days, literally. We can explore a more alternative and reduce the uncertainty. Why? We are going to spend more time, doing geological work, trying to understand the fault relationship, try to different scenarios, rather than really spending time on boring tasks like manual interpretation, as I mentioned. Okay, with this, the new assisted seismic interpretation using machine learning, and here I'm going to talk about this in Petrel as well as in Delphi. So we have two different approaches or two algorithms. We have the seismic fault detection and extraction using the faults, for fault interpretation, and also we are going to do machine learning interpretation for horizon interpretation. So it works for both horizon as well as faults. Okay, let's start talking about the interpretation using machine learning for fault detection and extraction. So the algorithm behind it is going to use a conventional neural network image segmentation. So it's based on imagery. The picture is going to be recognized, breaking down, and the algorithm try to understand the faults, what are the faults, and plotting them. So okay, think about it as image reconnaissance. Okay, for if you want to run a neural network, I'm not expert in that, but just think about it. So you need to first train a brain. Okay, you train a CNN, a conventional neural network, by feeding it different pictures. Okay, let's say I want my algorithm to detect this sign, this traffic sign. So I'm going to feed it hundreds, thousands of pictures, different pictures of this same object, and then train the model, or try to break down the model and then train the model using image segmentation in action. As you can see, image segmentation by breaking down different properties or different attributes of this image, so that the algorithm can at the end recognize the sign, the number on it, the different color, and tell me if it is a sign or not. So in seismic, we can do something very similar. Okay, we are going to train brains, using cloud data from the seismic data, so that the image is going to be reproduced and the algorithm can recognize where are the faults and do automatic interpretation. So we are just going to feed, after training the neural network brain, we're just going to feed the input data. It's a 3D cube that is going to go through a deep CNN, neural network, and then tell me where are my faults and where are my horizon in the cube. So the algorithm used for fault detection is an image segmentation algorithms that was initially developed in biomedical imagery by Ronenberg in 2015. You can find the reference here if you're interested to understand how it worked. But this algorithm was basically designed to try to automatically scan biomedical pictures. Okay? So this is a biomedical image. So the objective of the algorithm is to try to segmentate or to differentiate the different cells from this image and then count the number of cells automatically. Okay, so it's called the UNet. It learns segmentation in an end-to-end setting, which means a raw image in a ready segmented med output. It's a very few annotated images required for training, so you really need very few inputs so that the algorithm can detect the cells, the limits of the cells, and it's a very powerful tool to study multiple images, I would say. So imagine before people used to count one by one each cell in the imagery. Now it is segmented, as you can see, and the algorithm is smart enough to differentiate the different cell and then count them automatically. Okay, think about it about seismic. You have the same image. This is a biomedical image. This is a seismic 3D cube. So we are going to train the cube as an image and tell the algorithm where are my fault located in the seismic cube. And this can be a game changer for geophysicists, I can tell you, who are spending a lot of time doing redundant interpretation. Again, the reference is here if you're interested to learn more about it. It's already published and you can get it online. Right, so this is the algorithm we are using for fault extraction. Now, in the cloud, we have two options. You can rather do what we call a pre-trained fault estimation. That means you are going to take your seismic cube, feed it to the cloud, and then the cloud will do the rest. The cloud already have some pre-trained data set from open source data, sorry, and try to scan your seismic cube, I would say, and then try to extract the fault out of them. Okay, so it's a deep convolution. You are going to upload your 3D seismic cube into the cloud, run the pre-trained estimation using the deep convolutional network, and voila, that's the cube. You will get a pre-trained prediction cube that you can extract the fault directly. Now, there is another way, which we call the user-trained, and here it's more user-biased. That means the user is going to flag, you're going to give some initial model of the faults by labeling the faults, just labeling few sections. Think about it like 3-4 inline or 3-4 cross line only by just digitizing manually all the faults existing, just to tell the algorithm, okay, this is my fault, I want to trace it back to in the whole cube. Okay, so based on the user trained and then the model, the existing model, we are going to get the user trained prediction that you can also combine with the pre-trained. Of course, you can take the result from the pre-trained and try to enhance them using the labeling user trained. So we have two methods. We have on the cloud, we have what we call pre-trained automated fault extraction, which is just extracting the fault based on the models. And then you have the user trains, where the user is going to bias the interpretation more or less. Just a little bit more detail how the user trained prediction works. It's going to take this is actually also an image that is published. You can get the reference from here. You have the seismic cube. We need to just pick few fault labels. We don't need to do a whole interpretation. Think about it, about 2 or 3 inline and cross line. Then the labels are going to be fed into a vertical CNN neural network that is going to do the prediction in the inline direction and in the cross line direction. So it is going to sweep the cube in the inline and then in the cross line separately, and then finally merge the cube into a horizontal CNN to extract the faults. Just to give you an idea how accurate is this, it's going to really scan the cube in both directions, and then vertically and then horizontally, and then finally predict the existence of the cube. So as you can see, this automation of fault interpretation is going to change the way we do the fault interpretation and extraction. It's starting from fault labeling, and then we are going to obtain the cube evaluation size of a fault cube that we are going to extract, filter, and then directly feed to the fault framework. So this is a whole new workflow that we are not used to see. This is not what I presented at the beginning of the presentation, where you need to do fault sticks manually, horizon manually. You will rather take more time, spend more time in filtering and editing, and try to understand the geology rather than just repeating the job that is being done here. Okay, so let's try to see and break down each step to explain what is going on here. Okay, we start with the fault labeling. So with you just need to open your user trained fault protection, and basically by saying label, that means just flagging, the faults that exists in your inline and your cross line. You can have a limited number of inline of cross line, I repeat, and then based on these labels, the machine learning is going to build an automated fault extraction from the seismic cube. Okay. And then we need to go for a fault evaluation and extraction. So this is going to generate, once you run the model, it is going to take few 10 minutes. I don't know how big is your cube, but let's say 45 minutes for a small cube or 3 hours. It's already really depending on your seismic cube. So you're going to obtain a prediction cube with values between 0 and 1, where 0 is there is no fault and 1 is the existence of the fault. And as you can see, based on very few sections, you're going to obtain a predicted cube with the whole fault interpreted in one cube. So this is just one click. You just need to feed the seismic cube as well as the training label, and based on these two simple inputs, you are going to obtain a 3D estimation faults of your seismic data, which can be fantastic. The next step is the fault extraction. So once you do some quality check of your data, the fault extraction is going to be based on two parameters. It's the planarity and the azimuth. So of course the azimuth is the direction of the faults, and the planarity is basically the connectivity between the faults. So this parameter can help you to control, to have certain control of the connectivity of your fault network, I would say. So you need first to evaluate that, generate both cubes, and then extract the faults from your cube. This is how they looks. So we have the azimuth fault network, as you can see, as well as the planarity fault network. And instead of, okay, just ask any geophysicist around you how many time he's going to spend on interpreting each fault in this cube, I'm pretty sure he's going to say, let's say a week or a month, while here we can just do it in 3 hours maximum. Okay, think about it. You are going to save a lot of time. You are going to shrink your workflow or your workload from days to hours. And instead of just repeating manual process, you are just going to focus on the geology. You are going to do the geological interpretation, try different scenarios, and play with the different parameters to filter out the fault network and see what impact it's going to have on your 3D model in the next steps. So once you modelize the network of the faults, I mean the job is done. You just need to, you can merge, split fault point sets. You can filter extracted fault using some plot automatically, or you can simply show and hide fault closest to the peak just using a tool palette, as you can see here. And finally, this is the final step. We can finally convert the existing fault into fault sticks, fault interpretation by simple click. As you can see here, all this network of fault is going to be magically transformed into fault stick or fault interpretation that you can use in your modeling, or simply feed the model using structural framework and build a 3D structural model using structural framework just from the output of the points. So by the way, the output, as I said, the output is first prediction cube, and then the prediction cube is going to be extracted to points, as you can see here. And the points are going to be fed into the structural framework. So these are the different steps of the user-trained prediction workflow, as you can see. Okay, now we are going to talk a little bit more about the horizon interpretation, interpretation using machine learning horizon interpretation. So just as we developed the fault extraction, we also developed the horizon interpretation based on machine learning. You simply need to feed the seismic data here, and then you can use the horizon. You can use horizon training level. It's based in neural network, random forest tree, and using also radial basis function that is going to predict the existence and the continuity of the horizon and predict that automatically. You can also bias the interpretation using your existing fault cube. So the fault cube you just interpreted previously, you can feed it to the horizon interpretation to get more accurate and better interpretative results. Okay, this is how it works again. You are going to take the seismic SegWi cube and then add the fault estimated cube, okay, and run it in deep CNN neural network. And then you can also, of course, you need to start labeling. When I say labeling, this is very similar to what I explained on the fault extraction. You just need really 2 or 3 inline or cross line, and then combine, the labels of the stratigraphy with the estimated fault cube, and then you can automatically gate the stratigraphy. I can just show you one example here, how it works. You simply need to open the neural network horizon prediction inside Petrel, and then you put your seismic cube, and then basically just run it. Okay, it's that simple, really, 2-3 clicks, and you don't need to do more. This is one example showing you how the horizon labeling is going to give you the result from the machine learning based interpretation. Here, for example, we labeled 1, 2, 3, 4, 5 inlines and 1 cross line, and you see the result. How just by starting with few labels, you can quickly run a horizon interpretation automatically started from this using the neural network machine learning algorithm. So again, using manual interpretation to do this in Petrel, for people who are working on this, I don't need to repeat how long it's going to take, but pretty much a little bit more than 30 minutes, I would say, especially if you have a complex geology. While here you can really speed up the process by simply labeling 2-3 inline cross lines and run the process directly. Thanks to the machine learning, you can accelerate the horizon interpretation into your models. Okay, before concluding today's presentation, I would like to share with you some case studies. We do have some published case studies for using this new technology, and I'm pretty sure we are going to find a little bit more case studies coming in the future. So this one is okay in all 2020. As you can see, all the publications are pretty fresh. Application of machine learning assisted fault interpretation on large carbonate field with subtle through, and we all know how complex and challenging are the carbonate reservoirs. So the authors in this paper illustrate application of machine learning assisted fault interpretation in the Middle East, integrating a complex fault structure with the subtle through in a large carbonate field onshore Abu Dhabi. They used both PSTM time and PSDM depth seismic volumes in separate runs to confirm that the used machine learning technology is domain agnostic. So the fault interpretation labels made on 6 training lines. Okay, you can imagine. So they just made the fault labeling into 6 lines only, which is representing less than 0.8% of the available lines in the data set. And as you can see, they obtained fantastic results where all the faults were properly mapped. As you can see here, huge cube was automatically interpreted. I mean, the faults were automatically interpreted and extracted thanks to the machine learning new algorithm in Petrel. Okay, so the technology enabled rapid extraction of the complicated fault structure within a fraction of the time and effort previously taken using traditional means. So again, this method can also be used to QC your faults. Okay, this is something automatic. So if you are not sure about the fault existing in your data, again, it can help you to confirm if the fault is really here or not, because it's machine learning based and it's not human based. So as you can see, they used some filtering here and then extracted the machine learning they extracted the machine learning assisted fault interpretation and compared the results, the traditional approach with the machine learning approach, and the machine learning approach really helped them to benchmark or to calibrate the faults they interpreted. Okay, so the technology really enabled rapid extraction of complicated fault structure with a fraction of the time and effort previously taken using traditional means. This is the paper. If you are interested, you can find it online. Another case study from New Zealand this time. So the authors used machine learning fault interpretation and machine learning stratigraphies on the Upanke 3D seismic dataset over the Taranaki Basin in New Zealand, down under. Here is the map. This is New Zealand. This is the field where they used their study, and they used actually with 7 of 765 inlines and 23 of 2,233 cross lines. So imagine how big is this. Manually annotated, which is only about 1% of the available seismic data. Again, the labels they used is representing only 1% of the data. As you can see in this picture, this is the labels they used. Okay, even though it's a very complex geology, they successfully retrieved the fault as well as the horizon and really speed up the process. Again, I really invite you to read this paper if you want to really see, machine learning in action. How machine learning can speed up the process of the seismic interpretation, of the fault interpretation, horizon interpretation up to 80%. This is the reference. It's HiBeam in all 2020, accelerating seismic fault and stratigraphy interpretation with deep sea enhanced a case study of the Taranaki Basin, New Zealand. It's published in the Leading Edge, and I'm pretty sure you are going to see much more success stories and publications in the near future about these disruptive technologies. Okay, I would like to conclude my presentation on how can you use this, how are seismic interpretation assisted machine learning delivered. We basically have two deliveries. You can deliver it on the cloud directly on Delphi cloud environment. You just need a cloud subscription in Delphi, Geophysicist Plus, or Seismic and Seismic machine learning plugin, and then you can run it on the cloud. So now I know that in Algeria, for example, or many different countries, we still have difficulties using the cloud. Now the good news is it's also available on premise. That means you can just have it as a Petrel module or just as a Petrel plugin, and then use it in your own laptop, in your machine. You don't need to touch the cloud. You just need to download the plugin, because somehow we downloaded the machine learning trained machine learning brain for the seismic recognition, and now we can use it in Petrel, in your Petrel offline. Okay. Now the main difference between the on-premise and on the cloud is that the on-premise only user-trained machine learning is available. Of course, because you do not have access to the cloud data, so you can only use the labels. I mean, you can work on labels, and you can do the automated fault extraction using them on premise. While in the cloud, you can run the direct estimation. I mean, you just feed the cube onto the cloud, and then the cloud will do the rest. While here on premise, you really need to do labeling to proceed on the automated interpretation. It's available. It was released October 2023 in Petrel 2022.9 and 2023.3 as a plugin modules. Okay, so again, this is a very good example on how machine learning is going to change our habits, I would say, or how it can change the work for geophysicists, especially for fault interpretation and horizon interpretation. It's a process that can be really manual. It can take a lot of time, and thanks to the new machine learning technologies, we can speed up this process. Right, so with that said, I would like to thank you very much for your kind attention. I hope I was not very long, and we can take your questions if you don't mind. Thank you very much.
Thank you, Dr. Mohamed, for your presentation and the very, very insightful slides. I think it was very clear, and it showed very much how the technology of artificial intelligence can help in geosciences. I think this is one of the best examples that we can see. So, as you said, we can take questions now.
Thank you very much, Ahmed. Thanks.
Let's see the questions now, the commands. We have one command of and the command of Megalati Yunus, who said very short questions. Speaking about transfer learning, I don't know it was a command or a question, but I think you can answer that, Dr. Mohamed. So I'm not very expert in machine learning, so
I don't know what I mean by transfer learning. The question is not clear itself. So yeah, if we have clear questions, I mean, just type them into the comments, and then we can, or maybe yourself, Ahmed, if you have any questions related to the technology.
Yeah, I have some questions, but I prefer to wait. Okay, I'll ask my question. So, do you have any ways outside the machine learning model to quantify uncertainty about the results?
Yes, actually. Quantifying uncertainties. What do you mean by compare them with other inputs, or? Yes, good questions. Actually, yes, we can. Usually, what we do, as I said, the cube you are going to output is a predictive cube. Okay, so you have a prediction cube between 0 and 1, and of course you can use the existing interpretation. For example, if you have already interpreted manual faults, you do them, or in Petrel you can run what we call uncertainty analysis, where you can quantify the uncertainty of your cube. But again, it's all depending on the quality of your cube, because the input is deterministic. You're just going to have one seismic data, so that's really challenging to do some
quality
kind of
uncertainties with that. Yeah, and do you have any I may say some preference, if I may say, model or something like that can affect the results? For example, did you already try to compare it with some human-based interpretation, and you can see, for example, which model can give best results depending on
yes.
training
Actually,
data?
Yeah, actually, in the paper I presented, they already compared them. They compared PSTM with PSDM, and basically they gave them similar results. So, for PSDM is post-stack time migration and post-stack depth migration. They gave similar results. Now for the model, comparing with the model, yes, I mean, it was already all benchmarked, and already the training brains actually used for this. They use different basins from all around the world to train that. So yeah, it's already been done in the background differently. Okay, I think there's one interesting question from LinkedIn here. Does this means we don't have to use coding skills to perform the machine learning? No. Also again, no. We don't. You don't need to do any coding on this. It's really user friendly. You just need to understand how the algorithm works. Do a labeling of the false interpretation and then run it. Basically, you don't need to have any coding skill for this. This is really user-based algorithm. Okay.
Course. And okay, I'll ask another question. So, I think the models are not open source, so you cannot, for example, fine tune your model based on your own data, for example, or something like that.
So, well, basically, there are a few companies who already train their own brains, I would say, using their own data set. Just to name a few, Woodside in Australia, they already have their own already trained machine learning models. Now, if you have a huge data set, then of course you can help to train your model to make it more basin friendly, okay, or more
exactly. Exactly.
So you can. This is something always you can do to train it in parallel, okay.
Okay. And we have a question of
for Facebook, I think.
Just I have a question about machine learning prediction. I train a sample. We use binary data of presence and absence data of prediction, regression in spatial scale. Because I think by using special points,
each points have value. Yes, actually, this is imagery based interpretation. So basically, it works pretty similar to as I showed to biomedical imaging, where you have a picture, and then the picture is going to recognize discontinuities. In this case, it's faults, and it is going to be recognized and extracted. So, are we talking about binary? It's not really binary because at the fault level, you have a contact, but you have values between 0 and 1, existence or non-existence. So you can really trim or scale, the accuracy of the extraction. It's not binary, really binary. It's a predictive Q model that you can play with. Okay.
Okay.
Another one from LinkedIn. How will the algorithm honor the geology of the environment? It will perfectly honor it, because if the geology appears in your seismic, as far as it's appearing as fault in your data, then it is going to be extracted. You don't need to worry if it's a reverse fault, if it's a thirsting or it's a normal fault. As far as the geology is pictured, I would say, or mapped in the seismic, then it is going to be extracted.
So,
all right. So I think
last question, if you like.
Hello. Do I
expect the seismic waves? I'm not sure.
I don't understand this. We are talking about post-stack data here. I don't know what kind of seismic.
If you can clear again your comment, first, Saudi, and can Mohamed answer that? Maybe by messages. You can email him if you'd like. So, would you like to say something else, Mohamed?
Well, that's for me. Thank you very much. I would like to thank you for the opportunity. Stay tuned. I'm pretty sure you are going to have other speakers coming next to this one.
Of course, yeah.
If you have any other comments, Ahmed, before we can, although if we
again, I want to thank you, Dr. Mohamed, for giving us this insight today. And as you said, stay tuned for next presentation. We'll try to schedule another speaker, another experienced one on an IA in sciences. So stay tuned and see you next time.
Thank you very much, Ahmed.
Thank you again.
See you again. Thanks.